Hello, we are live. If you are here, say hi in the live chat, please. In the right place. Oh, hi, Theo. Hi, Anessa. Hi, Lillian. Hi, Isaiah. All right, flip this over this way. Good. Live stream 6. Okay. Hi, Cassidy. That's Liam. Good. Okay, good. Theo, Liam, Anessa, Lillian, Cassidy, and Isaiah is here too. Hello. How are you? There we go. Good. We still have a few people missing, Meow. Missing people are Isaac, Matthias, and Lauren. Can somebody send them a WhatsApp? That would be cool. Thank you. Just to see whether they're around. Okay, that's cool. Oh, that's cool too. Oh yeah, you betcha, huh? Okay. Hi, Lauren. Hi. Ja, sehr gut. Lauren is here. Jawohl. Okay. Alrighty. 9:03. We should probably get started just because we only have 30 minutes, and that's not that much time. Scooch the board over. Hang on. I have to leave and come back because it isn't loading on my phone. Okay. You just made 20 euros. Cool. How'd you get 20 euros? Liam, did you win a bet? Oh, you have a call at 9:30? Cool. Good. Okay. Well, we'll get started. We're recording this, obviously, so if the other people want to watch it later, they can. We are talking about power today, and we started that last time, I believe, but just a reminder about that, because sometimes you guys tend to forget. You sell jewelry online. Sweet. Good deal. Okay, so just a reminder about power. Power. That's what we're doing. And obviously, we're talking about electrical power because we are talking about circuits. Okay, and specifically, last time we talked about a little simple circuit like this. And we said, okay, let's just say we have a certain amount of voltage here provided by a battery, for example. Okay, so we have delta V over here. And let's say this is a 9-volt battery just for fun. Okay, I don't know if that's fun. Maybe a strange kind of fun. And let's say, let's just take 12. That's easier to divide. Let's do it 12 volts like this. Okay, and let's say over here we have a resistor with 3 ohms. I don't know. Those are the same numbers I used last time. Okay, so this is the lifting up of the ski lift. This is how much resistance there is, how difficult it is to get skiers down that slope, or kind of the inverse of how wide it is. If it's wider slope, then this number would be smaller, and more narrow slope would be a bigger number there. So first questions first, we got 12 volts of voltage pushing current through 3 ohms, right? So if we have that situation, we can figure out how much current there is. Okay, is related to voltage through this little equation, also known as Ohm's law. And some of you really like the Idiotendreieck. Then we can write it like this: delta V is there, I is there, and R is there. So we can find how much current flows through this circuit by using Ohm's law. Just type it in the stream to tell me how much current is flowing in this circuit. All right, you guys still there? There we go, 4 amps, good job. Yep, good. Very nice, very nice, very nice, very nice. So that would, of course, be delta V over R. That'd be 12 volts divided by 3 ohms. That is equal to 4 amps. So we have now two important numbers. We have the voltage is 12 volts, okay? And the current is 4 amps, okay? And it's important to remember. Oh, thanks for the update on your personal care situation there. Okay, so we have 12 volts. What does 12 volts mean? Just a reminder about that a volt is a joule per coulomb. Okay, a volt is a joule per coulomb. So if we have a battery with 12 volts, that means that any charge that comes out of that battery and flows through our circuit, that has 12 joules for every coulomb of charge, 12 joules per coulomb of charge. On the other hand, if you look at your outlet in Germany, we got 240 volts normally. That means there's 240 joules per coulomb. Okay, an American outlet, 120 volts, that will be 120 joules per coulomb. Okay, so this is a measure of how much energy there is per amount of charge. So 12 volts, meaning we have 12 joules per coulomb. Good. Let's take a look. 12 joules per coulomb. And now let's try to look over here and understand what this means. 4 amperes is the amount of current, and current is a measure of how much charge is flowing per second. So an ampere, we can write that over here as well. An am I still on the board? I sure am. Ampere. An ampere is a coulomb. I'm not sure where I'm going all caps here. Coulomb per second. Okay, or we can write it like this. I don't want to scooch off our screen. All right, we're still on here. So an ampere is equal to a coulomb per second. So if we look at those two relationships here, an ampere being a coulomb per second and a volt being a joule per coulomb, okay, so 4 amperes means 4 coulombs per second. Just to put that in words, if we take those two pieces of information, we can combine them into an expression. Just a reminder about that. We know there are 4 coulombs every second moving through our circuit, and we know that every coulomb carries 12 joules of energy. 4 coulombs per second, each coulomb carrying 12 joules. We can take those two numbers together and combine them into our power equation. The power equation says you multiply the current times the voltage difference to see how much power your circuit is delivering. So in our case, that would be power is equal to 4 coulombs per second times 12 joules per coulomb. And that would be 48 joules per second. And we have another name for that. That is a watt. So we have 48 watts of power being delivered by this circuit. You might have, we're not used to this anymore as much. Well, we do still use that. So when you talk about a light bulb, for example, you say, this is a 6-watt light bulb, 10-watt light bulb. We old people used to have incandescent light bulbs that got very hot, and they would be 60-watt light bulbs or 100-watt light bulbs. So they would use a lot more power than today's light bulbs. They would waste energy effectively by heating your apartment more than lighting it up. But this is a nice little power amount, 48 watts. I believe that was repetition of what we did previously. And I think that's how we kind of finished last time, but I think it's always helpful to kind of get a review just to make sure you're still on the same page. I'm going to take a picture of this, and then I will post it on our Google Classroom situation there. I got it. So, there we go. All right, so let's go. This one's going to go away, and this one's going to go away. And now we've got our little circuit there. So, and come back on screen over here for the top of this thingamajigger. We still have our 12-volt resistor here. We're going to now modify our problem just a little bit. Not sure I got the funny voice for some reason. I'm not sure exactly why. Here's my question for you. And specifically, the question I have is, we still have this resistor with 3 ohms here. Okay, now let's say we put a second resistor in, like one right there. Okay, and this, let's call this actually now R2, is this on the right side? And this is R1. And let's make it the same resistance. Whoa, crazy. That wasn't necessary, but let's just assume it is. Okay, so let's think about this now. And specifically, let's think about it in terms of 2 things. The overall current that is flowing through our circuit, okay, and the overall power in our circuit as well. So over here, we'll put our other Idiotendreieck, just so we have it ready to go. We've got P, we've got I, and we have delta V over here. There's our 2 equations. This one is Ohm's law, and this one is our power equation, and oftentimes we'll write it like this. There we go. Here are our 2 equations that we can use. And we look at this and say, okay, what kind of circuit is this, first of all? Is this, and I'll give you the words, is this a parallel circuit? Or is this a series circuit? Are you serious? I am serious. Is it a parallel circuit or a series circuit? It is parallel indeed. So the 2 branches are next to each other. So as a charge comes in, it picks one path versus the other. Good. Excellent. 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 So let's remind ourselves what this looks like in terms of our ski resort model. This means we're in a situation where once you get to the top of your hill, you have a choice of either going down one slope or the other slope, kind of like that. Okay, so you have a choice of going this way or this way. And then at the bottom, you come back up. That diagram works okay. Not great, but it's kind of okay. It shows basically, I'm going to choose a different color for the actual circuit. Stand back. I'm trying some pedagogy here. So make the circuit actually red to make it stand out a little bit better. So there's our ski hill. And we have a choice of either going down this way. That's much better. There we go. Or going this way. Oh yeah, that shows up way better. So this is the left one, R1. This is the right one, R2. And we have over here our power supply. And then, we kind of symbolize the charge by saying it's kind of like a skier that's being lifted by the ski lift. And then at the top, you have a choice of going down one side or the other. And of course, this is our ski lift, and it lifts us up a certain distance, delta V. Now, in this situation, we look at this and say, okay, we've got our two branches here. The overall lifting over here by the ski lift is 12 volts. So if your charge goes down R1, how many volts do you travel down when you travel through R1? How many volts do you travel through when you travel down R1? Volts being the equivalent of a height difference here. So tell me the answer to that. Theo says 12 volts. Okay, does that make sense, or does anybody think it should be 6 volts? 12, okay, Isaiah says 12 as well. Good. I'm just checking your understanding. 12 is the correct answer. So well done, team. So the point is you're coming down all the way. So in this case, it's 12 volts for all the charges. You travel all the way down to the bottom. It's going to be 12 volts for each charge. Okay? Okay, and Liam's not sure. Okay, so just kind of repeating a little bit here. The ski lift lifts you to the top of the mountain, and the height of the mountain is measured in volts. Oh, got it. Okay, good. The 12 volts both come down 12 volts. Excellent. Okay, so we have delta V is equal to 12 volts for 1, and it's also equal to 12 volts for voltage for 2, and also that's equal to the total voltage that's provided by the battery. Okay, so that means we can answer an important question here, namely, how much current flows through each of our resistors? So we have current flowing this path and current flowing down that path. And we'll call this I1, and we'll call this I2. So how big is I1 and how big is I2? Okay, Theo says half, and when you say half, Theo, I think you mean half the current goes this way, half the current goes that way. But what's the exact number of how much amperes, how many amperes travel through resistor 1, and how many amperes travel through resistor 2? Hint, it's the same number because it's the same resistance. Excellent wrong answer, Liam. Fantastic. Okay, so just a quick reminder, this is really confusing. It's easy to lose track of what we're doing here. So just relax, everything's going to be okay. So there's, 6 volts is wrong. 6 amperes is also wrong. 4 volts is also wrong. 4 is maybe right, but we actually need a unit on that, Anessa. Then we would be correct. Yeah, so you need a unit, Anessa. It's 4 what? 4 amperes. There you go. There you go. There you go. Good. I'm glad we're working through this because it is a little bit tricky. So just a reminder what the different things are we're looking at. So we're looking at a voltage or the amount of volts or a potential difference That's how high up you are lifted up by the uh, oh, don't be sad. It's good, Isaiah. So we're learning. So that's why it's good when you guys miss stuff. If we're going to meet online and talk for half an hour about this stuff and you'd get everything right, and it'd be like, what's the point? There's no point in doing this if you're not going to learn anything. Okay, and that's why I'm doing this, because I want to make sure you're learning it. And I'm glad actually you missed something, because if you knew this, I'm like, wow, that was a waste of 30 minutes. So okay, so this battery lifts us up 12 volts. You're increasing in height by a number of 12. In a ski resort, this would be 1,200 meters, for example. Now, 12 volts is how much you lift it up. And of course, in this case, when you go down either of the resistors, you go down 12 volts. That's the height difference that you're moving down. The current, however, is not that height difference. It is how many skiers, how many charges travel through there per time. And I1, okay, the amount of current depends on the voltage and the resistance according to Ohm's law. We have that over here. I is delta V over R. So I1 would be, of course, delta V1 divided by R1, right? I'm going to move this over just a tad. And then, of course, the voltage difference, well, that's 12 volts. Resistance is 3 ohms. Well, this looks familiar. That's 4 amperes. So we have 4 amperes flowing through resistor 1. We could do the same calculation for I2, okay? And then you guys could be like, well, Mr. Blessman, that's all the same. It's also 12 volts applied to this. The total voltage drop across here is 12, again, okay? So we should get the same answer there. So that means our left resistor has 4 amperes flowing through it. Our right resistor has 4 amperes flowing through it. So what is the total current, therefore, that's flowing through our circuit based on that information? And that's a question for you guys. What is the total current? The total current flowing. Okay, 8 amperes. There you go. It is 8 amperes. I kind of drew it in where you can't see it. Isn't that's great? There we go. So here we go. So we have a total current flowing, and it's kind of the equivalent of thinking about being on a ski trip, and you get together with your friends on the ski lift, and this part is the one we're interested in. 4 plus 4, correct. So how many friends do you have? Well, this is in this problem. That's what I'm saying. And the only information that you know is that 4 friends go down this slope, 4 amperes, and 4 friends go down the right slope. Okay? And of course, you'd be like, well, if we had 4 of us go this way and 4 of us go that way, that means the total amount that we were to start out with is the sum of those two. So I total needs to be I1 plus I2, and that'll be true always. In this case, they happen to be equal to each other, but this would be true if it was 2 and 7, 1 and 10, 6 and 312. Whatever these numbers are, these numbers together better add up to the total number of the current that is flowing, just as when you have a ski resort, the amount of skiers getting off the ski lift better be equal to the number of people that go down the ski runs and then meet up at the bottom again. Okay, so those numbers should be constant again at the beginning, here, and even when they're split, I total should be equal to I1 plus I2. So in our case, that would be 8 amperes. There you go. And we can write that over here. 4 ampere plus 4 ampere equals 8 amperes. Okay, so cool. Now, the question, of course, is in this situation, how much power do we generate with our circuit? How much light can we put in our room, assuming these are light bulbs that are creating light in our room, or they're chargers for phones or whatever it is? There's some kind of electrical device that's using power to do something. So how much power do we have in total in this situation where we have a parallel circuit? Well, we have power at resistor 1, obviously. Here. And also resistor 2 is creating power. There we go. Well, it's getting a little messy here, so we're going to kind of, draw that in red and blue. Okay, so how much power is created? Okay, cool, 36 amps. Okay, that's an interesting number, and it's definitely wrong, Liam. 96 watts. Okay. So that is the correct answer. And let's actually take a look and understand how that's being created. Now we have two equations over here that we should be looking at. Power is I times delta V. Okay. So for our resistor 1, right, we have and we have to figure out the voltage that, or the power potential difference that is applied here. It is 12 volts. Okay. And there are 4 amps flowing. Okay, so we can write that out a little bit and say, okay, well, let's do this. Wow. Pedagogy by color mixing. Look at that. I have a purple one. So P total is equal to P1 in red plus P2. And of course, red plus blue makes purple. See what I did there? That's pretty good, right? Hilarious. Okay, so let's write that over here. So we see P1. Well, our equation, reminder, is I times delta V. So we'll have I1 delta V1. Okay. Okay, well, that's 4 amps times 12 volts. Okay, and of course that means 4 times 12 is 48 ampere volts, and that has a name that's called watts. Okay, so we have 48. Okay, hi Isaac. So we have 48 watts of power being created by, being used by resistor 1. And of course, the same kind of calculation would also be writable for P2. And again, for P2, in this case, it happens to be the same amount. Okay, everything is the same. So we can say, okay, well, it's 4 amps times 12 volts. Oh, shoot, we should do this in blue. My whole point with the color mixing was to make this now happen in blue. So there we go. So we have here 4 amperes times 12 volts equals 48 watts. Okay, so then of course we see that our two resistors each create or dissipate or use, you can use different words here, 48 watts, and that means the total power, 48 plus 48, yay, pedagogy by color, is going to be equal to 96 watts. So in the parallel circuit, we've analyzed that a little bit. Now it happens to be a situation where the resistors are equal, but the same principle would apply in the case that the resistors were different. To answer Inessa's question, yes, the overall power of your circuit can also be calculated by the overall current times the overall potential difference. That is correct, and it is the same number. So in our case, because we have 12 volts and we have 8 amps of current flowing as the overall current, therefore our overall power is 8 times 12 is 96 watts. Either approach is appropriate, and of course then we could figure out how it's split between R1 and R2, and each one of those is using up 48 watts. Okay, cool. So I'm glad we got through that. I have some homework posted for you guys to work on the exact topics here, and keep working, keep learning some physics. I don't think I'll see you guys. You guys are all split up in science class with other instructors. So I hope you're learning some physics and or chemistry over there as well. But otherwise, I'll see you guys next week on YouTube again, same time, same channel, and I'll see you guys then. Bye-bye. Assigned is for the rest of the year, I believe. So I've assigned, I think, 4 more written assignments that takes us all the way through the end of school. Okay, bye-bye. Did I click beenden? I clicked beenden. Come on. Here we go.